Bismillahir Rahmanir Rahim. Hello students, welcome to the Electrical Engineering YouTube channel. Today I am going to start a new lecture series on the course of electromagnetic theory. This is a very interesting course which lies at the intersection point of physics, electrostatics and mathematics, including vector analysis. The contents of this course are vector analysis, Coulomb's law, electric field, electric flux, Gauss's law, divergence, energy and potential, current density and continuity of current, magnetic field, Biot-Savart's law, Ampere's law, Curl, Stokes theorem. And finally, time varying fields and Maxwell's equations will be discussed in this course. And for this course, the recommended book is Engineering Electromagnetics by William H. Haidt and John A. Buck. This is a very good book, and I can show you the preface of this book over here. So the PDF version of this textbook is easily available on the internet, and I am using 6th edition, but you can download any latest edition from the internet. This is the front page, and from this book, I will be teaching the chapter number 1 on vector analysis, chapter number 2, chapter number 3, chapter number 4, a few topics from chapter number 5, and chapter number 8 and chapter number 10. So these are all the chapters which will be discussed in this course. So in the start of this course, I will discuss the basic definitions of scalars and vectors and some laws which are associated with vector quantities. So scalars are the quantities whose value may be represented by a single real number, either positive or negative. And the example of scalar quantity is a temperature, potential charge, distance, time, humidity. These are all the quantities which only have the magnitude, and the second quantity is the vector, and the vector quantity is the quantity that has both magnitude and direction. And the examples of vector quantities are electric field, force, acceleration, magnetic field, velocity, and gravitational field. These are all vector quantities. Similarly, the scalar fields are a potential field around a charge, and similarly temperature field around a hot sphere or a hot boiling egg. So if we have a heater in a room, or if we have a hot sphere, then we will experience some heat around the sphere or around the hot element, for example, around the hot heater in the room. So as we go away from the heater or away from the source, the heat will become reduced. So this is the definition of a scalar field. So I will discuss some properties of vectors. So vector quantities obey commutative law for addition. They also obey associative law for addition. And in order to add two vectors, we have to follow head to tail rule, and according to head to tail rule, one vector is placed such that its tail lies on the head of the first vector. For example, this is vector a, this is vector b, so I will place the tail of vector b over the head of the vector a, and the resultant vector a plus b will be evaluated by joining the tail of the first vector with the head of the last vector. So this is vector a plus b. Similarly, if we want to subtract vector b from vector a, then we will have to first evaluate minus b vector and then add this vector a into minus b vector. So this is vector a, this is vector b. So minus b vector will be lying over here. Now put the tail of minus b vector over the head of the a vector, and the resultant vector a minus b will be evaluated by joining the tail of vector a with the head of minus b. So this is how we perform subtraction. Similarly, the distributive law is also obeyed by the vector quantities. R is a scalar and A and B are the vectors. So this will be equal to RA plus RB. Now the product of vectors can be evaluated by two ways. So if the resultant of the multiplication of two vectors is a scalar quantity, that multiplication is called scalar product or dot product. So the resultant is a scalar quantity. If the product of two vectors is a vector quantity, then the product is called cross product or vector product. Then it is represented by this cross. Similarly, there is another type of product which is called scalar triple product, and scalar triple product is written as A dot B cross C. So here B cross C will be evaluated first, and the result will be also a vector quantity, and that vector quantity will be evaluated as a dot product with A, and the final result will be a scalar quantity. So in a scalar triple product, there is no need to specify the bracket over here because uh, it is understood that on first this product will be evaluated, then the dot product of the resultant vector with A will be evaluated, because we cannot perform the dot product first and then the cross product, because if we perform the dot product first, the result will be a scalar quantity, and that scalar quantity cannot be evaluated to get a cross product with the vector quantity, so that is meaningless. So it means if we not specify a bracket over here, it's okay, and it is understood that first B cross C will be evaluated and the result will be evaluated as a dot product with A. So this is called a scalar triple product. There is another product which is called vector triple product, and the vector triple product is equal to A cross B cross C, and the result of vector triple product is also a vector quantity. Now, how do we perform dot product? So suppose we have two vectors. This is vector A, and these are its three components, and ax, ay, and az are the unit vectors, and the magnitude of these unit vectors is a unity, and ax, ay, and az are the magnitudes of a vector along the three axes. So w is equal to a dot b, and it is written as a b cos theta. A and b are the magnitudes of vectors a and b respectively, and a dot b can be written as a multiplied by b cos theta, and it is equal to a times component of b vector along a vector. So this is vector a, this is vector b, and the component of vector b along vector a is this b cos theta, and the component of vector b perpendicular to a vector is b sin theta. So while taking the dot product, we have to multiply vector a with the component of vector b in the direction of a. This is also called projection of vector b along a. Similarly, we can also do the other thing. So a cos theta into b can also be written as a dot b. In that case, a cos theta is the component of a along b, and this is the magnitude of vector b. So in that case, this is a vector, this is b vector. Now we have to resolve two components of a vector, and this is a cos theta, this is the component in the direction of b, and this is a sin theta, and this is the component perpendicular to b. So now we have to multiply a cos theta with b with the magnitude of b, so this will also be equal to a dot b. So practically w is equal to a dot b, so this is the a vector, this is b vector, and we have a dot product in between, and now we have to multiply all the components with each other. So the first product will be ax bx into ax dot ax. Now the second term is ax by into ax dot ay. So ax dot ax is equal to ax magnitude into sine 0, because the angle between x-axis and x-axis is 0. So this result is equal to 1. Similarly, ax dot ay will be equal to ax ay cos 90 degrees, and the result will be equal to 0. So while putting these substitutions in this product expression, we will finally get the answer as ax bx plus ay by plus az bc, as is written over here. So this is simply how we can perform the dot product. The second product is a cross product, and in this case z vector is equal to a cross b. This is the a vector, this is b vector. Now again we have to multiply all the components with each other. Now ax cross ax will be equal to ax magnitude sine 0, and this will be equal to 0. And ax cross ay will be equal to ax ay into sine 90. And again we have to specify the unit vector, or we have to specify the direction in which the resultant vector is oriented. So ax cross ay will be equal to az, and that product will be equal to simply az, and the product of cross product of two like unit vectors will be equal to 0. Now suppose this is vector a, this is vector b, and theta is the angle between them. So the direction of a cross b is perpendicular to the plane containing a and b. So the direction will be evaluated by using right hand rule. And right hand rule states that curl the fingers of right hand from first vector to the other, and then thumb will indicate the direction of the resultant vector. So in this case, this is vector A, this is vector B. So the thumb will indicate this direction, and this is out of the paper. So by following this rule, AX cross AY will be equal to AZ. So do we can perform this right hand rule over X, Y, and Z axis, and then we will see that AX cross AY is equal to AZ. Similarly, AY cross AZ is equal to minus X, and AZ cross AX is equal to AY. So in cross product, the commutative property doesn't exist. So A cross B is equal to minus B cross A. This is what we achieve by taking cross product of two vectors. Similarly, AY cross AX is equal to minus Z, and Z cross AY is equal to minus AX, and AX cross AZ is equal to minus AY. So by following these expressions, the cross product of A and B can be written as the expression over here, and this whole expression can be represented in the form of a determinant. So if we want to evaluate the cross product between A and B, first we have to specify unit vectors, then the components of vector A, then the components of vector B, and now we will take the determinant, and the result of this determinant will be same as is written over here. So this is a simple way of calculating the cross product of two vectors. Now the scalar triple product, which is equal to A dot B cross C. So in this case, first B cross C will be evaluated using this expression. Now when we take the dot product of this expression with A, these unit vectors will be replaced by the components of this first vector A. So the scalar triple product is also very important. If we want to check if three vectors A, B, and C are coplanar, we have to take the scalar triple product of these three vectors, and if the result is evaluated as zero, then these three vectors will be called as coplanar vectors. Secondly, if we want these three vectors are always substituting a parallelepiped. So if we want to calculate the volume of this parallelepiped, then we have to evaluate this scalar triple product, and that will give us the volume of the parallelepiped. So this is very important information regarding the dot product, cross product, and the scalar triple product. Now the unit vector of any vector can be calculated by dividing the vector with its magnitude. So this will be give us the unit vector of B. Now if we want to calculate the projection of one vector along the other, then we have to calculate the dot product of this vector with the unit vector of the second vector. So this will give us A vector into magnitude into the magnitude of this unit vector multiplied by cos of angle between them. So unit vector's magnitude is equal to 1, so it will be equal to A cos theta. So A cos theta is actually the projection of A along B, or component of A along B. Similarly, A dot AX is equal to component of A along X axis. So dot product gives us the component of a vector along the other. So this is one benefit of taking the dot product. The second benefit of taking the dot product is checking if the two vectors are perpendicular to each other or not. If we are given two vectors and we take the dot product between them, if the answer is zero, it means these two vectors are perpendicular to each other, otherwise not. Now we will check the benefits of the cross product. So here you can see we have two vectors A and vector B. Now these two vectors are actually constituting a parallelogram, and this is a parallelogram, and in the parallelogram, all opposite faces are actually parallel to each other, and there is some angle theta between two connected edges. So if this angle theta is equal to 90 degree, this will become a rectangle, otherwise it will be a parallelogram. Now the cross product and its magnitude is equal to AB sine theta, and that magnitude of the cross product between A and B will give us the area of the parallelogram. Even if theta is equal to 90 degree, that cross product magnitude will be equal to AB, and that will be actually the area of the rectangle. So cross product is used to check if two vectors are parallel to each other, and secondly, it is used to calculate the area of the parallelogram. So if the cross product of two vectors is equal to 0, it means two vectors are parallel to each other. So there are two benefits of cross product, and there are two benefits of the dot product, and there are two benefits of the scalar triple product. Now I will solve a simple example, and in this example, the purpose is to calculate a vector from one point to the other. So we are given two vectors p and q. So if we want to calculate a vector from p to q, which is rpq, then we have to subtract the coordinates of vector p from q. So these are the coordinates or components of vector p. These are the components of vector q. Now pq vector will be equal to coordinates of vector q minus coordinates of vector p. So it will be 2 minus 1 ax minus 2 ay plus 1 minus 3 az. So it will be equal to ax minus 4 ay minus 2 az, and this is a vector from p to q. So that is all about our today's lecture on the course of electromagnetic theory, and that lecture was related to the definitions of scalars, vectors, and some of the properties and product types in vector quantities. So hope you have understood the basic concepts of vector analysis. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.